what I'm going to talk about is we have lots of great talks about the details of performance. And what I want to do is take a step back and talk a little bit more about the sorts of things to think about before we write any code. What are the things that can help us to architect and design the systems so that they run with better performance right from the beginning? So this is kind of the only talk about performance that you'll probably hear where I don't say measure everything first, because you should be doing this at design time, and at that time you don't have anything to measure yet. So I'm going to break it down into a couple of things. And these are really things to think about. You should be considering them at design time. They're not rules, they're not principles, they're anything very grand. They're just a couple of ideas. And they're not the only things to think about. Everybody is going to be able to add to this list, but I think they're quite important things to think about. And when you think about them a little bit more deeply, I think you'll find that they're just really one thing, that it's very useful to break into two different parts, because they address different aspects of how we reason about our code and what we're doing. And these things are absolutely not new things. Unless you're completely new to C++, these are absolutely things that you think about all the time. All I want to do is just highlight that these are also things to think about, not when you have a performance problem that you're trying to solve, but actually something you can think about before you even write a single line of code or design or think about how your API should be structured. So, jumping straight in, we want to talk about, we need something fairly big to be able to talk about APIs. So one of the things that we have is we have an open source project called Falsegrass, which is a RESTful API wrapper around Postgres. And what it does is it allows us to take tables like the one here, which represents just a very simple little thing. It has a foreign key to a film, and we can attach tags to a film. And it takes a JSON configuration that looks a bit like this, and most of this you can ignore, but the get thing that is highlighted, that's the bit that we're going to look at. Fetching lots of data from Postgres and spitting it out over HTTP, and what a design for that might look like. So we can do a get. We've pattern matched the $1 on the URL tags, and we get a list of stuff coming out. Now, normally you would get this stuff out in CSV, which kind of looks like this. And CSV is great and all, except it's kind of difficult often to work out what's going on. If we've got numbers or whatever. So what we do when we do this is we use something called CSJ, which is comma-separated JSON instead of comma-separated values. And really, for the purposes of this talk, we don't need to worry about any of that too much. What it gives us is a great excuse to fetch large loads of data from the database and run them through JSON Stringify functions. So we can look at that. If anybody has any questions, feel free to ask them as we're going along, because probably the later stuff will work better if everybody actually follows the earlier stuff. So, and it will actually be easier for me if you ask them as we go along as well. So if I'm standing up here looking particularly stupid, I've probably forgotten what I'm supposed to say next, and a well-timed question will help. Okay, so what we're going to concentrate on is just the inner loop that is actually processing the record data that comes from the database. An inner loop that might look something like this. So we have a record set, we pull rows off it, we are going to stringify each of the fields. So we have an abstraction here which takes whatever data the database has and puts it in a JSON-compatible data structure. So when we iterate over the row, we get JSON coming out. and we can stringify that JSON. And it's kind of unfortunate, but half of our code here is just making sure we get the commas in the right place. There's, that's commas, isn't it? So what we're going to do is we're going to look at how fast we can make this. So I've got some stuff to run, which hopefully will actually turn up. Here we go. So I can do this, and I can look at our films table. So here we've got a table. It's got a few different types of fields. I've got about 400,000 films in here. Select count star from films. Where's my caps lock on? Yeah, 402,000 rows. They're all it's all downloaded from the MovieDB website. All of the code that I'm going to run is open source. So sometime after the talk, I will put some instructions. Anybody wants to try and reproduce these results on your systems and with other databases, it's free to do so. What does the data look like? Well, let's try and run something. So this is eq. We'll select with a limit. So we get this sort of thing. We have a header row at the top, and then we have the data coming out. And because it's JSON, not CSV, it's actually clear what these things mean. And the JSON blob at the end is just the actual raw data that came from the MovieDB. So we can do that, and we can time its execution very easily. So we have somewhere to start. And because we don't really need to see it all, and actually printing it to the console is kind of slow. So for all the timing tests, I'm just going to throw all the data away and just pipe it all into dev null, because we don't really care about the data. We're looking at the processing and the shape and the structure of the code that's doing that processing instead. That's not, oh, I still have the limit in there. No wonder it's so fast. Let's pull more than 3 rows. And it will spin for a little while. Dum-de-dum. Nine and a half seconds. It's amazing how long that feels up here. Okay, so looking at that code, so these are my backups just in case nothing worked properly. Hands up if the endler on here really bothers you. I mean, we're trying to make this fast, right? And we've got an end line there. What about the use of the OStream stuff? A few hands. Okay, we'll deal with the end line thing, but I'm not going to bother with the OStream stuff. But I will talk a little bit about the JSON type that we're using first. So has everybody used standard variant now? That's a bit new. Yeah, quite a few people. Well, some people, anyway. So at the heart of the JSON, we need to have something that can handle these different types that go into it. And JSON is made up of possibility of a null value, which for standard variant is represented by this mono-state thing, meaning one state. We can put bools in there. And then we're going to allow a couple of different numeric types. JSON is sort of associated with interop with JavaScript, which only has doubles. But there's nothing in the spec that says you can't put integers. And for a lot of the things that we use it for, having an actual integer type in the JSON is very useful, especially if you're pulling integers from the database. We have to have a string, and then we have the two slightly more complicated things. So we have a vector of, in this case, shared pointers. I think, strictly speaking, the shared pointer isn't required here, but it does make it a little bit easier to declare the types if you have this. And then we have an unordered map of strings to JSON as well. Now, the code that I'm going to show in the slides, the code that you just saw, is not the same as the code that I ran. Obviously, it's got all the rest of the stuff that it needs to connect to the database and print the header row and all that sort of thing. But most importantly, the JSON type that we actually use in our code is arranged a little bit differently to this. It implements what's called a persistent data structure, which is something that comes from functional programming languages. They're becoming more and more popular in C++ code. And I know Sean did a talk where he talked about using shared constant lists for undo, which is an instance of a permanent data structure. There was a talk at CPPCon where the Houdini developers were also talking about using structures which are clearly along these lines. So actually what we do is we just move the shared pointers a bit. And what this allows us to do is share large swathes. When we change one part of the JSON structure, all the unchanged bits get to be shared between all of the instances. And we can now copy a JSON value, and it's only going to cost us the increment. The maximum cost is going to be the increment on the shared pointer somewhere, or copying cheap things to copy like ints and bools, doubles, whatever. So, shall we remove that standard end line, and replace it with a /n? How much difference is that going to make? Has anybody got any ideas? Now's the time to guess. Yeah. Half a second, right? So we went from 9.5 to 9.0, yeah? So about half a second. So, all right, something, not bad. What we really want, though, is we really want something which is a bit better than that. So, these are timings from another computer. So, what are the two things that we want to actually deal with? Here is a very simple benchmark that is just allocating some memory. We want 10 megabytes of memory, or rather, our processing is going to make use of about 10 megabytes of memory. And we can do lots of small allocations, or we can do a few large allocations. And what you see is that as the size of the allocation increases, the total time drops down. Now you can see here in the column time per alloc that allocating more memory costs more time, but it's not a linear relationship. It's very strongly sublinear. So the time per byte goes from like 515 picoseconds down to 6 picoseconds. Each of those three lines, all of them are allocating a total of 10 megabytes, but we're doing it in different ways. So the first of the two things that I think you need to be thinking about is allocate memory as infrequently as possible. And of course, this has a profound impact on the shape of the APIs that we're going to deal with. And we can do the same thing for I/O. Here we pull in a vector. That second line is really nice in C++. You can't do that in one line and make sure everything is closed off, even in languages like Python. You have to have blocks and you have to have extra stuff to make sure that the file handles get properly closed. But again, we have a trial here. We're going to write the total of the 10 megabytes out to a file, and we're going to do so in various different sizes. And again, we see the same pattern. It's not quite as strong. As the size increases, the time per write does increase, and the total time kind of doesn't change between 16 and 512. And this is because the actual writing to disk actually has to happen. With the memory allocation, it's much cheaper for the operating system to deal with that. So the second of our two things is really the same sort of thing as the first. We're going to perform the I/O as infrequently as possible. And this kind of relates to a lot of stuff like I think it was Scott's talk this morning, was talking about batching writes for the cache at the CPU level. And these are really the same sorts of things applied across the entire sort of API space. So before you've even written a single line of code, you can think about how can we structure the APIs so that we don't need to allocate memory as often. I'm not even saying you need to allocate less memory. I'm just saying if you need memory, try and allocate it all in one go instead of allocating it a little bit by little bit. And then we do the same thing with the I/O. Instead of printing little bits at a time, here we call this standard C out several times here. We're printing just tiny, tiny little bits. So instead of doing that, try and wrap the writes up, and batch them so that you do this less often. And the core of our main processing, this Stringify function, is returning new strings all the time that we're printing and then throwing away. We probably shouldn't be doing any of that. In order to fix these problems properly, we need to change some APIs. So, stringification. Okay, so this is kind of, it's not the entirety of the code that we need here, but it's a good representative sample. We have the standard visit at the bottom, which instantiates a member of this class, and the variant will, whatever value type happens to be in the variant at that time, will get dispatched to the correct overloaded operator, of which there's a few more that I haven't included. So for a Boolean, we're just going to return the strings true or false. Pretty simple. And the null one, of course, is the same sort of thing. Double, we're going to toString it. And then for the array, again, we have this comma thing that we have to take care of. And we're going to recursively call Stringify on the items that we find inside our array. And the object one is very, very similar, except there's a bit more code because you have to deal with the key values too. There's a subtle bug in this. Does anybody know what it is? Standard toString is locale aware. And so if you actually do this on a machine which has like a German or some locale where the decimal point and the comma separators are swapped around, then this will not produce valid JSON. Instead of 1.5, it will print out 1,5. To fix that, that's not nice. There's a new C++ 17 char conversion feature, which I don't have on. Let's see me get this wrong. I'm compiling this on the latest Ubuntu, but I'm using lib standard C++ instead of lib C++, and it might be in lib C++ if I have the GCC and Clang ones the right way around. So what we're going to do, we can see here, each of these operators is returning a standard string. So we're going to allocate some memory, and we're going to return it, and then we're going to append these things together if it's something like this array, and then we're going to throw all these intermediate strings around. So we can reduce our memory allocations if instead of returning strings, we append to a string that we're given. So now we get rid of all of the intermediate stuff. So the bool now is plus equals. Now, of course, we have to deal with the commas in a different way because we can't look to see if we're writing into an empty string anymore. And this produces the same sort of thing. And sorry, Toby and Kate, we now have an out parameter. But, what can you do? OK, so this is the version that we had. And what we will do is we will convert it to this. So now we allocate, we have a string, which we use as a buffer. And we're going to write into the buffer. So now for the comma, we add the comma to the buffer. Stringify now takes the buffer as an argument. And then we append the /n. And if we're doing that work there to reduce the allocations, it's now actually also very simple to do the line printing much later. So we look, if the buffer goes above 60K, then we print the buffer out and we clear it. And because the last few lines might not add up to 60K or fall on exactly the right boundary, we have to do a final print of whatever's remaining in the buffer at the end. There's a sort of subtle thing here with the buffer clear and the buffer. Does anybody know what that is? Yeah, the comment was it frees the memory, and it's sort of yes and no. The buffer clear is not required to hold on to any memory that has been allocated. And this is kind of why there's no reserve. To start with, it's more space on the slides. But the reserve, you end up with this situation where you don't know where you should be reserving the string size anymore. If the clear actually frees the buffer, then you kind of need to do the reservation inside the for loop, or at least after the clear. And then it's like, well, if it didn't clear the buffer, and the buffer has grown because your size is maybe each row is about 100K, so you only end up printing one row at a time, then you might end up reducing and reallocating as you bounce backwards and forwards with larger and smaller lines. So it's not like vector clear, which does actually, the standard guarantees that the memory is held on to. With buffer clear, it does not. And I think this is in order to make the small string optimization a bit easier to implement. So we can try that. How long is this going to take? Is that quite disappointing? So when I was writing this code for the slides and I came to this bit, I was like, oh my God, all of the performance that I'm supposed to be getting, none of it exists. My entire talk has collapsed. But actually, it kind of proves, there's another way of looking at it, which kind of proves the point better. The standard library goes to great lengths in order to allocate memory less frequently and to actually write to the console less frequently. So all of our standard out is buffered. So it doesn't actually do anything, pass the data to the operating system to print, until that buffer is full. And the small string optimization means that we don't get as many actual memory allocations as we might otherwise expect. So in a way, we've got, what have we got between the three versions? The one, this select simple version that's still on the screen, this is as good as the standard library can do in order to reduce memory allocations and in order to buffer our output to reduce our number of times that we perform I/O. And this is the best that it can do, is to bring it down to 9 seconds. The extra half a second that we get is the stuff that the standard library cannot do because it has to operate within the confines of the API that it's been provided. So if you want to get the extra performance, you need to change the API. And we can get an extra, was it, 1/6 of a second, which is, what is that on 9 seconds? Somewhere on the 7, 8%, something like that? It's less than 10%, right? But more than 5. And that's, I mean, for the work that we put in, that's okay, but it's not great. Of course, in reality, you probably don't care that much. Well, depending on your use case, you might, but certainly for the stuff that we're doing, actually outputting this stuff where it just so happens that most of your string data is small enough to fall inside the small string optimization, and you are printing to, and you're outputting to a already buffered output, that's not actually something that we do very often. So a more realistic way of looking at how much performance applying these two ideas gives us is to take a step back and compare with unbuffered I/O and with data that defeats the small string optimization. So that's what we're going to do next. Oops. So this is just the same sort of timing information, but coming from a different machine. So we can run this unbuffered. And for the unbuffered case, I'm going to print this out once per line so that this keeps the logic here simpler. Yes, Titus, with some trepidation.
I'll be gentle. Have you run a profiler on these? Like, I have a suspicion that some of it is actually that cout has to be thread safe. There's clearly locking happening in there somewhere, and even
yes.
single-threaded, like that can't be.
That can't be completely free, right?
Right. And you
So he's talking about the.
Lighted all of that by doing buffering yourself and touching cout left.
Right. So Titus is talking about the locking that happens, and no, I haven't checked that. I'm not sure that it, I mean, we'll see, because we're going to keep using this standard cout in this way. So if it was all locking, then, or some locking, then maybe that would change some of the other results that we're getting. I don't know. So we're going to run something like this. This first line looks like some POSIX nightmare, but apparently is standard C++. And that is the official way of turning off output buffering on standard out. I know because it was on CPP reference. Okay, so we can run this unbuffered. So this version, we're still selecting from films which have fairly small strings that we're concatenating and dealing with. So we go up to about 11 seconds. So the I/O buffering, it's not a huge cost here. We're going from like sort of 11.1 to 8.4. So what's that? That's more of a, what is it, 20%-ish difference? Ish. But what we can do, because we're pulling this data out of the database, maybe we can find a table that has larger strings in it so we can see what the impact of removing the small string optimization has as well. Thankfully, I have something prepared, I believe. So, so this table is from Postgres' benchmarking tools, and it's an extremely simple table. This filler column is literally just that. It just writes in like 84 spaces. So there's nothing interesting going on in this data. Q. You can do a select. If I get my punctuation. What am I doing? Count star from PG bench accounts. So here we have about 2 million rows now. So let's try that. And we'll try that with the unbuffered first. Nope. That's better, I hope. Okay, and this is gonna take a little bit of time. Dum-de-dum-de-dum. Okay, 18.9 seconds. So we can pair that with the buffer time. Ten seconds. So here we're getting nearly a doubling in performance. And it's kind of a little bit sensitive to a few things like exactly how many big text fields you have. You'll get slightly more performance gain if you have more text fields than just the one here. So, okay, so the standard library, let's have a look at how much of that performance the standard library is able to give us. Which should be this. Oops. So it's kind of a little bit difficult to compare totally here because we can turn off the buffering and we can get comparable results across that. But we can't turn off the small string optimization without changing the data that we're testing. So we can't really see very clearly how much the small string optimization is getting. But the standard library does pretty well here. The output buffering gets us nearly all of the performance gain, but there's still like a good 10% there still to be won by changing our code. And of course, the buffering thing is kind of great if you happen to be writing to standard out, but I don't know what you guys are using C++ for, but for us, we are much more likely to be writing to a socket. And I think that the performance difference that we get by turning off the buffering on standard out is very similar to the performance difference that we get when we do this over HTTP, when we're doing this to a socket. It's not exactly the same because there's other stuff going on in different ways as well. But yeah, so we can take these two things, right? How often, let's try and reduce how often we allocate the memory, and actually we're reducing the amount of memory that we use as well, and reduce how often we perform the I/O. And, depending on how much of those two things you're doing, you can burn a huge amount here, doubling of the performance. You can burn a lot of stuff there. And these are things that need to be fixed in the API design itself. So it's not something that you can win all of this performance back by clever optimization of the function signatures as you're given them. You need to be willing to say, in order to get this performance, we're going to design around this. So what I kind of wanted to do as an experiment, if I go back to here, and again, this is just what we just saw. Yeah, this is just what we saw. So the code that we've just been running uses libpq, which is the official Postgres communication library. On top of that, we have libpqxx, which is the C++ wrappers for that. Then we have our false Postgres wrapper around that, which basically abstracts all the differences in the field types into this JSON type. And then we have the application code that we've written and run here, which spits out this data. So what I wanted to do was just do an experiment to see, okay, well, what happens if we take these two ideas and we design the entire communication with Postgres around them. So we design the library from the ground up with this in mind. What would that look like? So in order to do that, we need to know a little bit about how Postgres communicates the data, because we're going to connect directly to Postgres. So we have to understand the Postgres protocol. And there's a lot of stuff that goes on with establishing a connection and agreeing like what character sets you're going to use and time zone information, all this sort of stuff, and logging it. Going to ignore all of that. We're just going to focus on the communication that communicates the actual raw data to the application. So Postgres splits all the communication up into frames. I would say packets, but it's kind of an overloaded term. So I'm going to try and remember to say frame all the time. So we get the two frame types that are relevant to this, what we're doing right here. One is D, which is a data row. So the first byte will be D for data, and then we will get one C packet frame, which will say we finished, stop. We've now stopped sending data. C for command complete. Everything is done. Then every single frame has another 4 bytes that tells us how long the frame data is going to be. And it doesn't include the first byte in the count, but not that it really matters. And then for the data itself, we get all of the raw data. And the important thing here is that, or the simple thing for us, is that it returns it actually in text already for us. And we get things like how many fields are in this row, and information, there's some metadata about what the row types actually are and whether they have null values and this sort of thing. So we get a load of frames coming in, D, frame length, frame data, the next D, frame length, frame data, and then for the last one we get C, its length, and then a signing off message from the database. So we want to reduce the number of times we allocate memory, and we want to reduce the number of times we perform I/O. So we could do this. Let's assume that we can build the rest of the library so that we can use the data from Postgres directly. Don't know if we can or not, but that will at least give us a lower bound on how often we can perform reads and how often we have to perform allocations. So we can get a lower bound. So here, we can do one read for the first 5 bytes, and that will then tell us how much we need to read into the next part, how much we have for the rest of the row data. And then hopefully we can, through some magic, just make use of that row data more or less directly. And that's kind of okay, right? We're down to, what are we down to? 2 reads and 1 allocation per data row. So for the one that we just saw, that would be for 2 million rows, we're talking 4 million reads and 2 million allocations, which is, not terrible. But we can make use of the fact that we have this C block at the end, and we can strip one of the reads off. So now we can do 1 allocation for the body plus the 5 bytes for the next frame, and then 1 read for all of that. And then we move on. Now we can look at the last 5 bytes there to work out what should happen to the next row. And when we see the C frame at the end there, then we know that we're done, and we just read its body and nothing else will come until we talk to the database again. So that's better. Now we're doing 2 million allocations and 2 million reads. That's okay. And I kind of was sort of thinking that that was the best that you could do until I realized that I was actually being, there is another way. We could just allocate a big block of memory and then say, Postgres, how much have you got for us? and the kernel will just fill in however much it has. And then we chop it all up into our rows and field data from there. Now we're talking, how many allocations per row are we doing now? Well, possibly a very, very small number, depending on how big we allocate and how quickly Postgres is going to give us the data. Maybe we could be down to a handful or very few. So, what's the effect of that? So, this library that we have is called PG-Asio because it's built on top of Boost Asio. So, this is the PG bench one. Okay, so this is comparable with the line above it, 2.5 seconds. That's not bad. So compared to our slowest version, which was nearly 20 seconds for this, that's getting close to 10 times. And compared to the what you would normally just get through using the standard library, this is somewhere in the region of 5 times faster. And we can try it on the other data set as well. But I think if we're going to do that, I think we just want to remind ourselves of, okay, so this is the unbuffered one. So this is like, okay, we've turned off the output buffering. These strings are fairly small, so we're not going to see the full benefit there. So, okay, that was 11 seconds. So the question was, which one is doing work for the next?
If the PG-ASIO, after it read all it can read, it's actually starting to do work.
Okay, so the question is whether the PG-Asio version is doing work. You'll see there's a difference here between the real and the user thing. Between the real and user timing here with the unbuffered. This is the libpq version. And the default APIs in libpq and libpqxx, what they do is they stream the entire record set into memory and then hand it onto the application. So that's the delay that you see there. The PG-Asio version, because we are now in control of everything, we stream the data through. I will go into this in a bit more detail in a couple of slides' time. So, all right, so what's the PG-Asio version for this? Oops. .6. So that's more than 10 times there. Is it quite a lot more than 10 times? It is quite a lot more than 10 times, right? And actually what we do is we also take advantage of the fact that, well, Postgres is giving us the data as text. Most of this text is completely safe for use in JSON. So this record set contains a JSON field. So now we are not going to, why would we parse the JSON only to string it back out again? Now we're going to take advantage of the fact that Postgres gives us good data, and we just copy it to the output. So we can get a really nice performance improvement there. Oops. So again, this is just the same outputs. So this is kind of what the PG-Asio version looks like a bit. We have this block, because now we're going to read a load of data. And all of that data goes into a block, and it has some number of lines in it. We know from the record set how many columns wide it's going to be. So instead of doing a two-dimensional array of rows against columns, we can flatten this out to the fields. So if our record set contains 4 fields, we consume this field's vector 4 at a time and step along it. And the string views point into the data member. And you can kind of see this in the for loops underneath here. We go through the rows, and we go through the fields. Now, and then the processing function is also a little bit different, and it should pass the buffer. Yeah, the output buffer handling is not like that. It's still like the previous version. This is kind of okay. The problem with this whole thing now is that in order to read all this data in, okay, so we're going to allocate some large block of memory. Now, if a row happens to not quite fit in the rest of that block, what do we do with it? So this implementation takes the easy route. Doesn't try to do anything clever. What we actually do is we do the read into a separate block of memory, and then we copy the bits in until we get to a row that will no longer fit in this data member. So it's not as efficient as it could be. It's still doing a lot more copying than it actually needs to do. And all of the stuff where it is setting up the connection, none of that is trying to be clever. None of the rest of the implementation is optimized at all. The only thing that we've done is just said, let's take these two ideas, allocate less frequently, do I/O less frequently, apply them to the library design, and see what happens without doing any other work to it. And the timings of what you've seen is what happens. So that's all nice, but there's something that bothers me about this. And in deference to Sean, it's not the loops. The thing that bothers me about this is the data member. It's kind of just this ugly wart on the block, because what's it there for? It doesn't really contribute anything. I mean, we need it because we have to put the memory for all the data rows somewhere. We can't just leave it off. So, what I want is I want some new toys. Don't we all? Okay, so let's take a simple idea of a vector and a string view. And I'm going to use string view here because string view is really, really nice because it doesn't have a C string member. I like that. I'm a big fan of that. So, but at heart, both of them are basically, there's a lot more going on, of course, but it's basically just a pointer to some data and a size. So, what if we instead change those pointers to shared pointers? And if we do that, we could have a shared vector and a shared string. Now, the const inside that shared pointer is kind of critical. You really, really want this stuff to be const, because now you can share it between threads and you can do all sorts of stuff. You know about the long-term life of these things very easily, and it's easy to reason about. Yeah. And we can now do this sort of thing. So what we're doing here is we're going to take the shared vector and we're going to snap a bit off the front of it, an operation which is not very efficient with a standard vector. Pop front, you have to move all the rest of the data. Here we have something that acts like the pop front. It returns a shared vector of the first n elements, but we this shared pointer constructor underneath. Shared pointer has this really nice constructor where you can say, I have a pointer to this, but can you give me a pointer to this sub-object inside it, controlled by the same counter, the same shared reference counter? And we make use of that here. So we can break the first bit off by taking the shared vector of the data and the size, break that bit off. And then we replace our data member with the same pointer advanced S elements, which is what the data get plus S does. So actually these two pointers, the shared pointer data underscore and the data underscore dot get, the raw pointer at the end there, are unrelated, and they can actually be of completely different types with shared pointer. And then we return the head. And if we had something like this, then our block would could just look like this. It's just a shared vector of shared strings. And this is, to me, a much, much neater sort of affair now. And I get another benefit in that if in my processing, I want to actually keep hold of some of these strings, I don't have to pay for an allocation for those either. So now my loops, the inner one is massively improved because I'm just going over the little bit that I snapped off the top, but I still have to do this split thing in the outer loop. But I'm pretty sure there's going to be a thing in the ranges that will let me take a view of n items across something like this that I can use instead. And the shared vector and the shared string are kind of nice as vocabulary types as well. Here, and I'm pretty sure this is completely valid. What I'm doing is I'm creating a shared vector from a standard vector, and I capture its size, and then I create a new shared string from its data pointer, and I move the vector into the closure for the deleter for the shared pointer. So now I've completely type erased that standard vector. What's even nicer is that I've completely type erased the allocator that the standard vector was using. So it doesn't matter where you got this memory from. I can put it into a shared vector, and now I can slice and dice this shared vector very, very efficiently. I can copy it, and it's going to be const, so I know I can share it between threads safely, and do all sorts of other nice, cool stuff with it. So, one final thing that we can do. I don't quite have enough time, but I do have another version that I can run, which takes the processing. Are you able to see these numbers? Yeah, it's not so bad on this screen. The PGSIO CSJ version that comes with the PGSIO library takes these blocks, and because we've now got this sort of block bit in there, we take advantage of that and we process those in parallel across multiple threads, then tie the data back together again at the end. And as you can see, this is running on my desktop. The multi-threading gives us even better real time for approximately the same amount of user space time. So we're doing about the same amount of computation, but now we get to do it in less wall clock time. So we get our results faster. So that's it. War memory allocations, war on I/O, and build your designs around this. For best effort, think about it when you're doing your design and build everything around these ideas. And that's it. 2 things.
If I understood that correctly, how long are all of your allocations living during your processing? Like, you have certainly fewer allocations because you read these big chunks off of the network.
Yep.
Right. How long are those big allocations out there?
For the amount of time that it takes to process a block. I mean, in these examples that we're running here, that's how long they last.
Okay, so wouldn't you do just as well not having all of that synchronization on upping and downing the atomic ref counts in your shared pointers by just saying, I know that the block is going to live, or the allocation lives as long as this block, and doing all of those things with just string view? I'm not sure that I buy the last step that you took.
Yeah, I mean, so the reason for doing that is just that it gives me a much more regular, much more simple to use API, where the API user doesn't need to concern themselves about the details of which bits of memory go with which things.
Yeah, that I would buy, but...
And you're right, the ref counts cost, but I'm kind of thinking of this in comparison to returning standard strings, and the ref counts are always going to be cheaper than the allocation. So, when you've got that, you could reduce where the ref counts go as further optimization. But the big win here is in the reduction of the number of times that we're allocating to start with. Now we can sort of argue about the details of this implementation might be a little bit faster than that. We can fiddle around with those details. And you could probably get another couple of speed ups. But I like the big win at the front. That's the thing that attracts me. And with these shared counts, I still have a very nice to consume API. I can very easily build a pleasant API on top of that.
Right, but if we're, I mean, a very nice, very pleasant API, except for the edge case of I held one of them.
Yes, exactly. And so I think what you would do if you were actually doing this for production code is you would have something like shrink to fit, and you would put that on the shared string, where you know that you want to disassociate the data that's in the shared string now from the data that might have been carried with it previously. Used in the same way that we do with standard string shrink to fit. Maybe you even call it shrink to fit, I don't know. But I think that would deal very easily with that case.
Hey, thanks for the talk. Wouldn't it make sense to lazily iterate on the string views? Like in the example you had, if instead of storing the string views in a vector and then iterating on the vector, you would have a function which gives you the next string view from the previous state. Wouldn't you eliminate all the allocations on that vector?
You could do. I don't know what the consuming API would look like there. And in a post-coroutines world, great. In a pre-coroutines world where you have to do all of that stuff inside out, I'm not sure that I want to write that code. I mean, it's just messy and nasty and easy to do wrong. So for this experiment, let's just do it the simple, easy way.
Thanks for the talk. I was wondering while you were discussing the use of memory and reducing the number of memory allocations and so on, did you consider splitting the idea of using the buffer versus filling the buffer, where you have a buffer that grows to as big as you need it, or just keeps growing to big enough for each record or whatever, so that you can just fill it and only allocate it once and then use it to process it and switch back and forth, or just use a few of them for however many threads you're using or whatever.
You don't know how big the record is going to be until you've done the read.
Yeah, you just...
So there's sort of an ordering problem there, I think. Or have I misunderstood what you're saying?
A little. Some of the Microsoft APIs talk about getting the buffer, and then it'll say you didn't have a big enough space to do it.
Yeah.
Give me more. You could do something
so
similar
we
to that, where you could grow it to be big enough.
We could elide
and just keep it.
We could
growing.
elide a lot of the copies. At the moment, we just have a separate buffer that we do, and then we copy it into the block. We should really be doing the read straight into the block, but then you've got this sort of bit left over problem. And again, for this experiment, I just didn't want to deal with it. You know, there's plenty of stuff that you can do to this to make it faster. The interesting thing to me was, what does just doing the bare minimum, is that a worthwhile thing or not?
So you said the reason that you avoided std string was because of the SBO, basically doing things when you're clearing, right? Or was that the reason?
No, it's about the wording in the standard. So if you have a vector that is grown to be 100 elements and then you clear it, the capacity of the vector is guaranteed to be the same after clear as before. After resize? Okay, there's an argument going on, but in any case, with standard string, there is no such guarantee.
I think that all the...
all of this, like, in the previous meeting, so don't
Okay.
plan on it.
Yeah.
I think all
Don't plan on it.
I think all the implementations of std string still don't deallocate when you clear. But
So most do not. I think that like the big implementations don't. I believe there are some which do, because it makes the small string optimization much easier to implement if you can assume that the data doesn't need to be deallocated if the size is 0, this sort of thing.
okay. And the other question I had was, why didn't you just pass an allocator to std string?
You could do, You could do. I mean, so the shared string, of course, you can type erase the allocator, so which is one of the things I like about that sort of idea. And you can. So if you're going to change the allocator, then that's still like a change to your API, right? You're no longer able to use standard string. You're using like PMR string or some other string thing. And if you're going to do that, then why not just blow the whole thing wide open and do it? I don't think that you can get, I think you can get most of the way there with allocators, but I don't think you can get all of the way there. You still have to do something like the reference counting somewhere, I believe, but I'm not an allocator expert. And one of the other things, which is the other thing I like about the shared string version, is that if I talk to our junior developers about allocators, everybody just glazes over. This shared string stuff is relatively easy to understand. Even people who are non-C++ developers get it. So that to me is another big win in its favor.
Thank you for the talk. Just more theoretical, just for better understanding of the title of the talk and with APIs. So in your talk, the API is some internal use, because it looked more like implementation detail. And if the library is exposing some functions or API as an interface for the user for database requests. So, and then in talk we were more discussing the implementation.
Yeah, I mean, so the implementation, of course, is closely coupled with the API boundary that you expose. So if you really want to make the implementation much more efficient, you have to let the API boundary change. And you have to change it and build the API boundary around what it is that you want to do. So if you don't care that much about performance and you just return standard strings, which might be large ones and have to be allocated, then that's fine, probably for lots of things. If you're doing a library where you do care about the performance and that makes a difference, then probably you need to design your APIs around how can we do this less? How can we pass in and reuse a string or something like that? Okay. Thank you, everyone.
All right. Thank you, Kirit.